All right, good morning, everyone. I was told yesterday that you have a construction midterm and a big assignment due Saturday, so I expected perhaps attendance would dwindle a little bit this morning. Just to remind everybody, what we're talking about in this particular class at the moment is we're talking about tension members. And ultimately what we're doing right now is we're just looking at different ways that tension members can get ripped apart in such a way that we might get full or partial collapse of our structure, okay? So we're not looking at the design of anything yet, just looking at what could go wrong with our tension members. And once we've seen all the things that could potentially go wrong with our tension members, we'll start to put these pieces of the puzzle together to figure out how we actually design something like this, right? This is structural steel design class. We haven't done much design yet, but unless you know what can go wrong, it's very difficult to figure out how you should be designing something. We talked briefly about, okay, now my pencil doesn't want to work. Oh, because I'm on eraser. That would be a good thing to off of. We talked about this expression when we introduced tension members. That's the easiest thing you can do. We want to prevent gross section yielding so that we get excessive elongation of a brace. Excessive elongation of the brace can cause instability and ultimately collapse. And we spent a lot of time talking about this expression, which is net section fracture. We talked about what the net section might be for a simple arrangement. We talked about what the net section might be once we start to experience or encounter staggered bolts, how we have to consider different potential failure planes. And then last day, we talked about the subscript E component, which had to do with having not the entire area effective in tension, because we only typically tend to connect certain components. Practically speaking, we can't connect everything all the time. And so we looked at the shear lag effects and how that can reduce the net area when we talked about net effective area. The scariest equation on this particular slide is one in the middle, and this is what we're going to start talking about today. Despite the fact that this is a scarier equation, it's no more difficult than net section fracture. In fact, I think net section fracture, as far as the tension limit states goes, is probably the most difficult thing to deal with. So we're going to only spend today talking about this expression. And so the purpose of today is to talk about what goes into this equation in particular and what it represents. Here we're going to talk about a failure mode called block shear failure. And so far we've talked about the resistance of tension members, and so it seems weird for us to think about shear necessarily. But what we're going to see is that based on how the bolts are arranged, we're not just going to have potential failure planes through faces that only experience tension. It's also possible to have failure planes through faces that experience shear stresses. If you want more information on this, there's quite a bit of information in the recommended course text. If you've bought it, you can look at chapter 3.4, which is on block shear failure. There's also a reasonable amount of information in the commentary, and so handbook section 2 is the commentary to S16, which is section 1. You can go look at the commentary to the clause we're going to be talking about today. That's quite helpful. And I've posted a journal paper to the course website. If you're super interested in where some of the stuff we might be talking about today comes from, you can go and take a look at that, and I'll mention that a little today. Basically, we're looking at a situation where, in addition to having failure perhaps on a particular face in tension, it's also possible that once we rupture the face in tension, instead of going all the way out through the rest of the component in tension, it's more likely in some situations that we may just tear the rest of that steel out through the two faces that are going to be experiencing shear stresses. We call this block shear failure because it basically comes out as a rectangular block, and there's a combination of tensile stresses on the tension face and shear stresses on the shear faces. Okay, so we're going to be looking at a combination of what can happen when we develop these kinds of shear and tension failure planes, how we can add these two components together, ultimately calculate the resistance. Okay, so basically we're looking at something similar here. It's almost the exact same thing, but just slightly different. Basically, again, we're going to be looking at situations where we get this tension failure and combination of shear failure. And so we're going to be looking at how we can model this kind of behavior using simple expressions to capture the combination of these two failure faces in terms of how we might quantify the net resistance associated with that kind of failure mechanism. We could possibly experience the same thing. It's possible to also have block shear failure happen when you get some kind of stagger involved as well. Basically here we have the face that we might be considering in tension on a stagger, and we might be adding an SRT over 4G term or two to consider the staggering there. In this case, we might also have a shear stress on the last little bit of that block coming out. And so again, we have a combination potentially of failure of different faces in net tension or in shear, and we have to figure out how we can add these components together to quantify the resistance of this kind of failure mechanism from happening. So basically, after today, you should be able to identify when block shear failure might be something to check, and basically identify different potential failure blocks through bolted connections. We're going to see that there's lots of different ways that we can get a block pulled out, a block shear failure, and ultimately we have to figure out which one's critical. You should be able to calculate the net tension and gross shear areas for block shear failure and select an appropriate tension efficiency factor. I'll tell you what the tension efficiency factor is all about. And ultimately, the goal after today is to be able to calculate block shear resistance for a bolted member that's in tension. Okay, does anyone have any questions about why these three things might be important to us for this course before we get into the technical material for the morning? It's not like broken record sometimes. I like to repeat some of the words just exactly the same. Don't mean to bore you that way. But it sounds like we're good. So let's start to unpack this long and somewhat ugly equation. It's not that bad once we start to dig into it. Basically, what we have is a combination of stuff happening on the shear faces and the tension faces. Okay, so basically we're trying to figure out how we add the force we get from the stress on the tension face and the stress on the shear face together so that we can calculate what the resistance to this kind of failure mechanism might be. Because this is a fracture type failure mechanism, it's brittle, we don't get a lot of warning signs before something like this would happen. We're using the same resistance factors we did for net section fracture. That's to make sure that it's more rare that something like this would happen compared to something like cross section. On the tension face, there's not a whole lot of new stuff here. We have there shouldn't be an E here, so get rid of that E in that equation. I might come back here and also get rid of the E, it should just be AN. We have stuff that looks somewhat familiar to us. So ANFU, that's a tension force, right? The only thing that's new here is we have a UT factor. And so I'll tell you when UT is going to be anything other than 1. A lot of the times it's 1, and so we don't really have to think very much about that part. The other part that comes into play here is the shear face. And so there are a few different things going on. One is we're calculating a gross shear area for the considered failure block. I'll tell you how to do that. And the failure stress in shear is basically this 0.6 times the average of Fi plus Fu over 2. Does anyone remember perhaps where this 0.6 might come into this expression from when we're quantifying these things with respect to ultimate tensile strengths? I'd mentioned perhaps way back in lecture 2, is there anyone who might think of, or anyone who might remember where this 0.6 might come from? 0.6. Well, basically, these are tensile failure stresses, right? Yield and ultimate tensile strength. Looking at the development of shear stresses on these faces, and we might remember that the shear yield stress is about equal to 0.6 times the tensile yield stress. That comes from failure theory, which I didn't present necessarily in lecture 2, but I gave a nod to the fact that when we start talking about failure of steel and shear, we're looking at using the same tensile properties. We're going to be multiplying that by 0.6 to convert it into a shear property. So we got 0.6 to convert a tensile strength to a shear strength. That makes sense because we're dealing with shear. What's weird is that we've got this Fy plus Fu over 2 term. Why are we not using Fy? Why are we not just using Fu? Well, there are a couple things going on here. First, I'm going to talk about what AN and AGV are and how they're calculated. And then I'm going to come back and talk about why we're using this average of Fy plus Fu in calculating the shear resistance on the shear faces. Basically, what we're going to do is we're going to simplify the failure mechanism here. The net area and tension is pretty straightforward, except we have to recognize that this AN, when we're doing these calculations, is different from the AN that we've calculated before. Before, when we looked at AN for flat bars or any other sections, we took the gross area, we subtracted the bolt holes, and that was the net area and tension through the whole section. AN, when we're doing block shear calculations, is just the net area that we're actually expecting to experience failure on a tension face. And so AN for some sections might be all the way through here, right, in terms of the complete net section fracture. But when we're dealing with block shear, we're just focusing on the development of tension on the face that's likely to fail in tension. So tests have shown, generally speaking, that we start to experience yielding on the tension face, we start to experience yielding on the shear faces in some kind of pattern that's not straight lines. But what we do is we model that essentially as straight tear-out lines through the steel here. And we'll also recognize that when we're calculating the shear area, we're not taking away any bolt holes here. The shear area is actually tangent to the opening of the bolt hole. And so this is called the gross shear area. So far, we're very used to calculating net areas by subtracting bolt holes. We do that for the AN part. We use the distance between bolts, and we subtract the bolt hole diameter to account for the distance between the two and the removal of the steel in that area. When we're dealing with the gross shear area, we're not subtracting any bolt holes, and so we're using center line dimension of the bolt to the edge of the plate. And so in this case, we've got a total of half the shear area on the two sides here. And so when we're considering the shear area for a failure plane that looks something like this, we're going to calculate the shear area on this side, and we're going to calculate the shear area on that side. We're going to add them together, and that's the total area that's experiencing shear on that particular failure plane. Okay, does anyone have any questions about what's new here in terms of calculating net area and tension? What's new with respect to calculating gross area and shear, and why we do or do not subtract bolt hole diameters for either of these calculations? Okay, so that's the shear area and the net area and tension. Again, very important here. If you do a net section fracture calculation, you calculate AN, it's not the same AN that you plug into this equation. The next part here is, what the hell is this? Fy plus Fu over 2. That seems a little bit weird. Basically what happens here, and perhaps I'll also remind everyone about some of the stuff we talked about in lecture 2, not only is the steel going to be slightly weaker in shear, right? We multiply the tensile strength by 0.6 to get the shear yielding strength. It's also more ductile. And so it takes more strain to develop the shear stress, or the ultimate shear strength, that it does to develop the ultimate tensile strength. What I mean by this is that as we pull this block out in tension, we're going to develop tensile stresses here, and we're going to develop shear stresses here. And generally, because the steel is more ductile and shear, it takes more strain to develop the ultimate strength. We're actually going to reach the ultimate strength of the steel in tension before we reach the ultimate strength of the steel in shear. And so we might have something like this for tension. We're going to have something like this for shear. And so the ultimate strength for the shear faces is here. The ultimate strength for the tensile face is here. And so what's going to happen is we're going to actually reach the ultimate strength and tension first, and we're going to fracture the face in tension. That's going to immediately reduce our carrying capacity before we develop the ultimate strength of the face in shear. Okay, so this is the ultimate resistance of the member. And even though we can still add a little bit more force over here to achieve the ultimate strength in shear, we've already achieved the ultimate strength of that particular member, and so we cannot really take it full advantage of the ultimate strength of this particular component in shear. So to summarize, the ultimate strength of the member occurs or is achieved once we reach the ultimate strength of face in tension. On the shear faces at that time, they're yielded, but they're not reaching the ultimate strength. They're somewhere in between the two. Okay, so at that time, the stress on the shear face is somewhere here, which is between Fy and Fu. And so we just simply take the average of those two to account for the fact that the stress on those faces at the ultimate strength of the member is not quite at the ultimate strength in shear. Okay, does anyone have any questions about that concept, or why we're using this average of Fy and Fu in calculating the corresponding resistance from the shear faces? Okay. So back in the day, we didn't used to do that. And so in the state and in the Canadian standard, 2001 and before, we actually looked at a couple different things. So we used to look at the net area and tension, which never changed. And then we either used the gross shear area times Fy, or we used to use a net shear area and multiply that by Fu. And we took whichever one was smaller. And that's annoying because, well, we're never actually going to achieve the fracture strain or stress at the same time in tension. And we have to now calculate two resistances every time we want to calculate block shear failure. So that's annoying, and so we don't do that anymore. And in this paper here, out of some researchers from the University of Alberta, you might recognize Conde and Kulak here from the textbook. Robert Driver is a professor just retired at the University of Alberta, very famous people in the structural steel design field. They basically evaluated this expression, and so they're the ones to say, well, Fy plus Fu over 2 divided by root 3, which we convert to multiply by 0.6. This was what was introduced in 2009, and so we continue to use basically the same expression. That saves us from calculating two different resistances dealing with Fy, the gross area, Fu, the net area, and basically we combine them using the gross area and this average of these two strengths. And so you can get some more information on the stuff I was just talking about here with respect to adding these together and considering the development of the stresses on the different failure planes and shear and tension. If you want, you can go and take a look at that paper that I've also posted to the course website under the same folder. Does anyone have any questions about what we're trying to do here? Basically what I'm saying is we've got a face in tension and we've got faces in shear. We're not going to reach the shear strength at the same time we reach the tension strength. The ultimate failure happens once we fracture the tension face. And so we use this expression to account for the stresses present on those two faces and add them together based on the corresponding areas to calculate the corresponding block shear resistance. Any questions about what we've talked about so far before we see how we might apply this? Okay. So block shear tends to be more prevalent when we start to look at rolled shapes. And the reason for that is it's just more likely to govern compared to net section resistance. And so I'm going to show you a few different examples of how we might apply this to different kinds of situations. Okay, so it's quite common, as I mentioned the other day, if we're dealing with channels as tension members, they might be a brace, but they're more commonly used as some kind of head plate anchor in like a telecommunications context. We bolt the web of the channel to the gusset plate that we're transferring the tension from. We very, very rarely, and I would say never, when we're looking at channels as tension members, connect the flanges. It's just not practical. The web sits nicely up against the gusset plate, and so we tend to drill holes through the web and bolt that to the gusset plate. We already looked at how this might fail in net section fracture on Wednesday. Now we have to look at what might happen if we could potentially develop a block shear failure pattern. I've gone through and perhaps misguidedly gotten rid of your necessary, I've gotten rid of the need for any of you to do any real thinking about how to calculate the block shear resistance in this case. And what I mean by that is for a certain number of fasteners and for a certain spacing and for a certain pitch and end distance, it's pretty much always going to be the same calculation. And so I've parameterized basically the calculation of these areas for you, so you don't really have to do a whole lot of thinking about it. Let's just say this channel has 6 bolts through it, and they're arranged in this kind of pattern. We've got a gauge distance, we've got a pitch, and we've got an end distance I'm going to call E1. Basically, if we know how the bolts are spaced and we know how close they are to the edge, it's very simple for us to go ahead and calculate the shear area using this expression here. And what's going on here is this parameter F is just the number of transverse line fasteners. We talked about that the other day. Lines of fasteners or bolts. And so why we have F minus 1 here? Well, in this case, we're likely to pull out a block that looks something like this. We've got tension in red here, shear in blue here. And that's what's shown in the rectangle here on the right-hand side. And so when we're calculating the tension area, it's pretty easy for us. We just take spacing, the center to center spacing, and then we've got half of bolt hole diameter here, half of bolt hole diameter here. And so the net area and tension is going to be the gauge distance minus 1 bolt diameter multiplied by the thickness of the web W. Okay, so that's for a situation like this, how we'd calculate the net area. When we're looking at the shear area, again, pretty straightforward. We're going to have an edge distance on both sides. And because we've got 1, 2, 3 transverse lines of fasteners, here F is equal to 3, we have 1, 2 spacings, right? So on the right-hand side here, we're going to have F minus 1 times P plus the edge distance. And because we have 2 of those, we're going to multiply that by 2. And we're going to multiply that by the thickness of the steel that we're feeling that through W. Okay, so if you've got 4 lines of transverse fasteners, it's just, the picture's going to look a little different, but you can still use this expression. You just use 4 instead of 3, as long as the pitch is consistent, which it always should be. If you're detailing this properly, then you can use this expression to figure out what the shear area would be. Okay, so once we know what those are, we can plug them into the expression. And in our case here, we're just going to be using a tension efficiency factor of 1. And I'll tell you a little bit why you might not use 1 in a second. Does anyone have any questions about how we might approach calculating the shear area for something like this, how we might approach calculating the net area and tension for something like this, and how we might use that in the expression we introduced so far to calculate the block shear failure resistance? Quiet, quiet, that's okay. So like I mentioned in lecture, I don't know, at this point, 12, I think, it is possible that we might stagger bolts. I mean, I can maybe count on one hand the number of times I've seen bolts staggered for, well, for anything really, but even for a channel or something like this. But it is possible. And so if we were to stagger this, not only do we now have to consider the stagger on the tension face, but we're also going to be adding on a little bit more shear area on one side, right? So over here, we're going to have P and P, but now down here, we basically have S plus E1, right? So staggering the bolt on the one side increases the length of the shear plane on this side by S. And so we have the 2 times the F minus 1P plus the 2E1 plus now on the one side, we all have that staggered distance. And so our shear area is going to increase a little bit as well. So the net area and tension increases due to the stagger. Shear area increases slightly due to the stagger as well. What we've done here now, though, is we've also done something else. The other thing that we've done is now made the failure block slightly asymmetric, right? There's now more shear area over here. So the shear force on this side of the shear block is going to be bigger compared to the shear force on this side of the block. There's more area, there's more shear force. The load applied is essentially just going to be through the middle, or more specifically, I guess, technically through each of the bolts, but the resultant force through each of those bolts is more or less going to be through the middle. Basically what that means is, if we consider equilibrium now, the tension force on the failure plane on the net area tension is not going to be centered anymore, right? The resultant force on the tension failure plane is not going to be centered, because then we wouldn't have moment equilibrium, right? We've got a bigger force over here, a smaller force over here. Where do you think the resultant force on the tension base is going to want to migrate towards to restore moment equilibrium in this situation? To the left, right? So we need more force on the left to maintain moment equilibrium. So the resultant's going to be slightly shifted to the left. What that means is that the resultant stress is going to be slightly skewed towards one side. And what that means is we're actually going to start to fail part of the area in tension first, and that's going to lower the ultimate resistance associated with that potential failure plane on that base in tension. To consider that, we're going to apply now this UT factor. UT is a factor that accounts for a lack of symmetry on the failure plane and the eccentric nature of the stresses that will develop on the net area in tension. So calculating this is something that we need to do. I don't even think there's an equation out there for us to try to calculate it. What the researchers have done to date is they've said, well, we've looked at a bunch of different cases where we might have asymmetry in the block shear failure mode, and to account for that asymmetry, we are going to apply this factor, and it comes from testing. And so it's a factor less than 1 for situations where a failure block is not necessarily symmetric. And so for the most part, they're just going to be tabulated in the standard commentary. So in section 2 of the handbook, go take a look there for different kinds of UT factors. But for something like this, I would recommend for staggered bolts where you are introducing a slight asymmetry in the shear faces, we're going to be reducing the efficiency of our tension face for that case. Does anyone have any questions about what's going to happen if we stagger bolts in terms of increases to the net area and tension in the gross shear area, and how that might require us to apply a tension efficiency factor not equal to 1 in a case like this? This stuff must just be too easy. So I just want to show some fun pictures. This is a test of a channel that did have a staggered bolt in it. So there was 1, 2, 3, 4 bolts in a rectangular pattern, then a last bolt out. And so in this case, we might be doing something like this. I mean, here we might have 2 staggers, 2s squared t would be over 4g terms. And then we have a shear area that's similar. In this case, the shear area is just through these 2 components. And so this is a situation where the stagger didn't necessarily add to the shear area because the bolt's not over here. It's centered. And so net area and tension is here. Our gross shear areas are here and here. And that's what the pulled out failure block looks like. So generally speaking, they found that considering the stagger, using this term plus the to increase the net area and tension generally corresponded with the strength that was observed through testing in this fancy finite element analysis on the right-hand side here. So this approach was generally shown to work okay. I don't think I posted this particular paper. I don't think it's important for you to go read it, but I'm sure if you really wanted to read it, you'd find it using that reference. So that's a channel, and I spent too much time talking about that, but we might also have an angle. And so it's quite common for us here to bolt our angle by a single leg with a single line of bolts. You might, from time to time, if the angle is quite big, use 2 lines of bolts, but whatever. In our case here, we're just going to focus on an angle connect with a single line of bolts. In this case here, it's quite similar, right? We've got 1, 2, 3, for our case here, transverse lines of fasteners. And so the shear area is F minus 1 times P. And we've got the edge distance here. And because the leg thickness is T, we're going to be using T as the calculation, right? This is T. And so there's not a significant difference here in the shear area, except we have 1 of them, compared to the shear area for the channel here, where we had 2 of them, with this being W, web thickness. In our case here, though, what's happening is now there's a really big asymmetry in the presence of a shear face versus the tension face. And that's going to cause a significant amount of additional twisting on that tension face. In fact, it needs to develop significant additional stress, basically to try and restore the moment equilibrium acting on that cross-section. And because of this high level of eccentricity due to the fact that we have a single shear face and a single tension face, we get penalized more heavily on the tension face component of that calculation. Okay, so now we have a significantly less efficient tension face, so we apply this tension efficiency reduction factor of 0.6 to the net area and tension when calculating the block shear failure load for something like this. Okay, so because there's significantly more eccentricity on this type of connection, we have a lower UT value, but in terms of gross shear area and net tension area, they're very similar. Here we've got E2 on the tension face. We have 1 bolt hole here, and we're only looking at the center to edge distance, so we take away half that bolt hole diameter. So we end up with E2 minus half bolt hole diameter times T on the tension area. Basically, this was observed also through experimental and numerical research. So we've got some tests on the left and tests versus fancy finite element analysis on the right. And basically, they experienced tensile fracture very early on when they were looking at the block shear resistance, and so they were able to corroborate this reduced tension efficiency factor of 0.6 when calculating the block shear resistance for a bolted angle carrying tension. So anyone have any questions about differences between channels and angles, why we have this quite reduced tension efficiency factor for a situation like this, or how we might calculate the net area and tension or gross shear area for an angle with a single line of bolt through it? Okay. I'm going to look at WTs now because they're a little bit more interesting. WTs tend to be bolted by the flange to the gusset plate. Never, ever, ever bolt the stem. If you do that, you'll look silly in front of everybody. We always bolt the flange of WTs in our tension measures. In our case here, we almost have something that looks like an angle, right? On the angle, we had something that looked like this, rectangle on the left-hand side. But now we've got basically two of them. So we have the potential to pull out the edges, basically, of our WTs here through here and here, through shear and tension on those two faces. Despite the fact that we basically have two blocks, or a block here that looks like the angles, and a block here that looks like the angles, because there are two of them, we're restoring some symmetry. Okay, so even though we've got edge tear that looks like the angle, there's significantly more symmetry involved in a situation like this. However, it's not perfect. And so in this situation, we're going to basically be using a slightly reduced efficiency factor compared to one, but it is going to be bigger than one that we use for the angles in this case. The reason for that is when we combine the two together, they're basically mirror images of each other, so there is some symmetry here to help restore some moment equilibrium to those failure blocks. Basically, in this case, we're just dealing with shear areas and tension areas that are very similar to the angle, except they're multiplied by 2 because we now have 2 of them. That's one way that we can get block shear failure in WT, and probably it's the most common. But there are other ways that we could get block shear failure. We might get block shear failure something like this, where we fracture the entire flange in tension over here. Or, well, in addition to tearing the stem of the web in shear, what that looks like is something over here in the middle, where we've got shear on this part of the stem that's getting torn out, tension on the face of the flange that's being ripped apart. And so that's going to change slightly the net area and gross shear area calculations. If we look at the rectangle, the net shear area is basically this, right? We're using W for the WT section multiplied by the length, so 2 times P times E1, so F minus 1 times P plus E1 times W. And on the tension face, we basically have the flange area, which is T, multiplied by width of the section B. And then we subtract the bolt holes from that to figure out what the net area and tension is. This is surprisingly symmetric, despite the fact that it's kind of a weird shear area here. The shear area is more or less, I mean, it's very close to the center of the load, and so researchers have generally recommended that we continue to use an efficiency factor of 1 in a situation like this. The most complicated one and the least likely is something that looks more like this. It's possible that we have sort of a combination of this one, where we tear a few different areas in shear, and so now we're dealing with tearing out this area in shear, this area in shear, and this area in shear. And so we're basically taking this expression from the first failure mode and this expression from the second failure mode, and we're adding them together here. And then on the face and tension, now we're just dealing with the gauge distance minus half bolt hole diameter here, half bolt hole diameter here. And so we have gauge minus bolt hole diameter times the thickness of the flange in tension. Again, we're using a UT factor of 1. And I've presented these this way on purpose. This is the most likely to govern. This is the second most likely, and this is the least likely. But similar to net section fracture, depending on how you're connecting things together, it's very possible to have more than one potential block shear failure plane that you have to assess. There's no way for us here, because we're adding shear strength to tension strength, we can't just compare the relative areas and automatically know which one is going to govern and which one's not. But this one tends to govern more often when we're looking at the block shear failure resistance of WT section. Okay, does anyone have any questions about how block shear resistance might apply to WTs, why we might have these different potential block shear failure mechanisms that we need to consider, and how we go about calculating the gross shear, net area, and shear and tension respectively to quantify the block shear resistance of a connection like this. When I say this one's more likely to govern than this one, what do I mean by that? Any ideas? When I say that this one's more likely to govern, what I mean by is that when you calculate the tensile resistance using the block shear expression, I expect it to be significantly less than the tensile resistance I'd calculate for block shear resistance using this kind of failure mode using the same equation. Okay, so this one's going to have a higher resistance associated with it. This one normally has a middle resistance. This one normally has the lowest resistance, but it really depends on how the bolts are arranged, and so you do ultimately have to check all three to be sure which one's going to govern. You might say, Taylor, why did you not tell us about this when we were looking at this flat bar brace? And the reason I did tell you about this when we were looking at this flat bar brace previously, this is the same arrangement from lecture 10 when we started looking at net section fracture and gross section yielding. Basically, if you just go through the equations and for the two different situations here, I'm pretty sure I have the blocks arranged correctly, but there are two potential mechanisms for block shear failure. There's one similar to ripping out the WTs at the edges, and there's one similar to the channel where you rip out the plate in a rectangle that looks something like this. For these two failure blocks, if you quantify the resistance, you get something close to 2,000 kilonewtons for both of them. Do you think block shear is going to be a problem here for us for this flat bar brace we've calculated other resistances for when we're getting resistances of near 2,000 kilonewtons? What was the resistance of this flat bar brace? Does anyone remember? It was a lot less than 2,000, right? When we calculated the gross section resistance, we got 709 kilonewtons. When we calculated the net section fracture resistance, we got 587 kilonewtons. That's like 1/4, right, of this one. So block shear for flat bar braces, you can basically wipe it away. We call that by inspection. It's very unlikely that block shear is going to fail a flat bar brace like this because we need enough bolts, the shear area gets ridiculously long, and so it's just not likely to happen, and so you can usually ignore for flat bars. The last thing I'll say before we get into a quick example here is it's possible from time to time that you might experience some kind of tear out behavior where we do not have a net area and tension failing, and this is basically where we might have some bolts and they're close to the edge. And this is shown in the test that I did at McMaster for the steel class back in 2014. Basically, you just rip out the little bit of area in shear. So here we've got some edge distances E1. We basically have, well, if you have more fasteners, we basically just have 4 times E1 if you have 1 line of fasteners times T. As you get more than one fastener, this is very unlikely to govern. And so it's rarely something that's going to govern if you have a well-detailed connection. But if you're in a situation where you need to check that, you can just ignore the tension component. It ends up being a conservative check because now we should be achieving the ultimate strength of shear because there's no area and tension to consider. But S16 in the commentary says that we can quantify a resistance against tear out using half of the equation where we ignore the tension part. Does anyone have any questions about why block shear failure is really not much of an issue, flat bar braces, when we might need to check it for a poorly detailed connection like this against tear out of the bolts just straight through and pure shear, and how we might apply the expression in either of those situations? Okay, so we'll get into an example here then, and I think given time, I'll just probably go through the first parts of the example instead of trying to turn it over to you to try and work through it. Basically, we're just dealing with a new member now. This is WT. It looks something like this, except now there's just 4 bolt holes instead of the 6 that we have previously. And so in 3 dimensions, this is what it looks like. It's connected to some kind of gusset plate like this, and it's carrying a factored tension force. And what our goal here is to calculate the factored block shear resistance for this connection. Does anyone have any questions about what the example is trying to get at before we start crunching some numbers? What's the first thing that we should be doing when trying to calculate the resistance of a hot rolled section like this that's given, WT 155 by 30? We know that we're ultimately going to be using this equation, right? Can we just start applying this equation? No, we don't. We might have Fy and Fu if it's 350W steel. UT depends on the failure block we're looking at, but first we need to figure out what the net area and tension and what the area and shear will be. Because we're dealing with WT, we're going to have to look at a few different failure modes. We're only going to have time to look at one, and so we'll look at the one that's most likely to be critical, which is this one. And we can calculate AN, which is based on T, and AGV, which is also based on T. And we also have, I guess that's pretty much it. We have T in these equations. It means we need some cross-sectional properties, right? And some properties I failed to give you the other day. For this section, on page 648 of the handbook, we have T is equal to 13.1. If we need it, W is equal to 7.5. These are all in millimeters. If you want to calculate the net section fracture mode, which I do in the extended example notes that I've posted to the course website, we've got 3,800 millimeters squared. Okay, there's some other properties that we may need, but we don't need any more of this currently to do these kinds of calculations. All right, so basically for this, before we can use the equation, we need to quantify the net area and tension, and we need to calculate the gross area and shear. So here I can just apply the simple expression. I've got more or less the same arrangement, except for me, I've got a different line of transverse fasteners, but this arrangement, at least for the area and tension, is very similar here. In this case, I'm given some spacings. I guess in this case, I do need B. And B, I have equal to 203 millimeters. And the reason I'm saying I also need B here is because I'm not explicitly given this E2 value, right? I need to figure out what this E2 value is here, and that's based on detailing of the connection. It's quite common to give the gauge, but not actually give the spacing or the edge distance on the drawings. So the first thing I need to do for AN calculations is calculate E2. That's going to be B minus the gauge distance for me here divided by 2, right? Because I've got the gauge, which is 120. I've got half the remaining area on either side. And so that's 203 millimeters minus the 120 millimeters over 2. And so an edge distance that I'm going to use for this calculation is 41.5 millimeters. All right, so I've got E2. That comes from the geometry and the cross-sectional properties. And I can calculate the net area and tension using 2 times E2 minus a single bolt hole diameter multiplied by the flange thickness. The drawing here says I've got 21 millimeter diameter holes, and so I can use that number. The net area and tension is 2 E2 minus bolt hole diameter T, which is 2 times 41.5 minus 21 times T. I guess I should write T out there. T is equal to, oops, I don't want orange. 7.5, sorry. T is equal to 13.1 millimeters. Okay, so the total net area that I'm expecting to fail in tension, in my case here, is going to be just 812 millimeters squared. Okay. Does anyone have any questions about how I got this number, why I needed to get this number, or what that number represents for our block shear resistance calculations? And not difficult math, it's just you have to know how to set everything up for us. Okay, so we've got AN, right? That's this area here, fail in tension. I need AGV. AGV is the blue lines here, and so I'm going to have P multiplied by the number of transpastors minus 1 plus the edge distance. I am given the edge distance here, and that's one that's typically given on the detailed drawings, just because of the way that the people have to figure out how the drilled holes are going to line up. So I can calculate my AGV here. I guess I'll be consistent with the equation. So basically we've got, and maybe I'll make myself some space. We've got 2 times the number of transverse fasteners minus 1 times the pitch plus the end distance multiplied by the thickness T. I just realized now, oh, that's good. Everything's good there. In my case here, if I come back to the example, I've got 1, 2 transverse lines of fasteners. The pitch is 80 millimeters, right? So I've got 80 millimeters on either side, so I've got 1 times 80 on both sides. So this is going to be 2 times 1 times 80 millimeters plus 40 millimeters times the flange thickness, which is 13.1 millimeters. I get an AGV value of 3,144 millimeters squared. Okay, does anyone have any questions about how we got that number or what that number means when we're with respect to calculating the block shear resistance of the connection in this particular failure mode? Okay, so we've got our AGV, we've got our AN. Now it's just time for us to apply the big ugly expression. The only other thing here that we need, right, we know Fy and Fu because it's 350W steel. We know the resistance factor is always going to be the same. The only other thing that's important here is our efficiency factor. Basically, from the commentary, if you go to the commentary on block shear resistance, they're going to recommend using a value of UT of 0.9 because it's symmetric, but it's not perfectly symmetric when it starts to get ripped out in terms of the way that the stresses develop. A bit of hand waving there, but that's sometimes how things go. We're going to quantify tensile resistance then as phi U times UT AN FU plus 0.6 AGV Fy plus Fu over 2. We have 0.75, UT is 0.9, AN is 812 millimeters squared, FU is 450 MPa. Continuing the big long ugly equation on the next line, we've got 0.6 times AGV, which is 3,144 millimeters squared, times 350 MPa plus 450 MPa over 2. Crunching everything out in your calculator, and I recommend that you try it. There's nothing worse than seeing this done on paper, and then all of a sudden you're in the exam and you're trying to get the brackets right, and the addition right, and the square roots when we start to see them. It is good to try and put this into your calculator. But when I crunch the numbers here, I get a value of 813 kilonewtons. Okay. Does anyone have any questions about how we used AN and AGV in combination with the other parameters here for this expression to arrive at the conclusion that we might experience block shear failure in tearing out the edges of the flanges in a way that looks similar to what's shown on the slide here, and what the value 813 kilonewtons might mean in terms of factored tensile resistance? So there's some other ones here. I recommend that you try them. I do have the example note though. For the second potential failure mode, basically on slide 17 here, going through those calculations, we end up with 874 kilonewtons. Give it a try or look at the example. And for the final one, we end up with 1,066 kilonewtons of tensile resistance. Based on those three numbers, which of these block shear failure modes is going to govern the block shear failure resistance for this member in tension? The first one, second one, last one? First one, right, of course. 813 is a smaller capacity, so we're more likely to get block shear failure through the first failure mechanism. less likely for the second one, very unlikely for the third one. Doesn't mean they're impossible, but they're just less likely. And in the limit states design framework, we take the factored resistance of 815 kilonewtons to represent the block shear failure resistance of this example connection. Does anyone have any questions about this example? What we were able to accomplish, would still be left to accomplish to arrive at those other two numbers, or why we arrived at the conclusion that the one that we checked was in fact the governing block shear failure mode? So that's just the way that the expression is formulated, right? And so basically when we look at the potential failure mode through these kinds of situations, that's not the right, there we go. So it kind of looks like the holes kind of get elongated or whatever. So technically it could be the net area in shear. And like I said, historically we checked the net area in shear on the ultimate strength, the gross area in shear on the yield strength. Basically in this paper, they found that using the gross shear area with the average Fy and Fu when converted to shear gives a better reliability, and so it estimates the resistance well. It doesn't mean it's exactly what's going on, just is a good estimation of the resistance when we apply the gross area instead of the net area. Cool? Just by what? Yeah, basically. I mean, like, you can do finite element analysis or testing. Basically, they did a bunch of tests. They estimated the resistance. The estimates corresponded well to the test results with a high level of reliability when using the gross shear area. Okay. All right, well, now you should be able to identify some potential failure blocks, different kinds of bolted connections, calculate net tension and gross shear areas for the block shear failure mechanism that is appropriate, and select the appropriate tension efficiency factor, and ultimately calculate block shear resistance for a bolted tension member. Okay, does anyone have any questions about anything we've talked about today so far, or why these three things are important moving forward, before we wrap lecture up for the morning? All right, well, enjoy the rest of your day. Have a good weekend. Good luck on your construction midterm, and we'll see everybody on Monday first thing.